motion. Introduction. So the purposes of this lab was to observe an object with projectile motion and also to compare the differences between these projectile motions that we're going to be graphing. So we're going to have a model with and without drag, including gravity in both of those, and then also the experimentally tracked data. The main result of this lab was that we found that the computer's model trajectory without drag was very inaccurate compared to the experimental trajectory, and with a non-zero drag coefficient, as in including a drag force, it was more accurate but not completely. So the basic physics ideas and equations are Newton's second law. We use this to derive our two of our formulas. We have velocity update formula and displacement update formula, which you can see in the pictures, and here for velocity update I also derived it. We also have the drag formula, which is equal to negative bv squared v hat, which is going to be drag coefficient, negative drag coefficient times speed of the projectile squared times the unit vector of the projectile. The assumptions that we have, our main assumptions is that drag and gravity are only forces acting on the projectile. This is important because the way we calculate net force, which is like the sum of our forces, would be incorrect if we didn't sum a third unknown force. And also another assumption is that we assume our tracker data is accurate, such as the ball's position, every frame, the axes, and the calibration stick. And not really an assumption, but the system of our experiment is the ball being thrown as a projectile, and the surroundings is everything else. Here we have the video of the tracker data. You can see each frame. Here we have the tracker stats. The most important of the tracker stats is this table that we're going to be using for our code. These are just two graphs of like the X and Y positions as time increases. Here's the code. So the modified code is that I adjusted the mass to be of the mass of the ball, 0.0035 kilograms. I adjusted the position to be just the x1 that you can see in these tables, the table that I was talking about earlier. The velocity vector is the initial velocities of the two positions, the x and y positions. We calculated that using this formula I talked about earlier. The v average is equal to delta r over delta t, which is just like x2 minus x1 over delta t. And the same thing for y. Delta t I said is 1/3 over 10, which is 0.033 repeating. That's because 0.033 just itself wasn't really working, so I had to change it. Here I have the two b's. One of these was commented out for each one. When b is equal to 0, that means there's no drag being modeled. And then when b is equal to 0.001, we're saying that's our drag coefficient for the formula I'll talk about over here. Here, this formula that I just mentioned was f drag is equal to negative b times the magnitude of the ball's velocity, so the speed squared, times the unit vector, and I get that formula from here, like I was talking about earlier. The f drag is equal to negative b v squared v hat, and then f grav is 0, negative mg0 as a vector. F net is the sum of f drag and gravity. The ball and velocity formulas I coded from these two formulas I talked about earlier. The arrows I just said was the arrow scale times the unit vectors of the force of gravity, drag, and velocity. The code output, you can see here that without drag, it should have reached the ground a lot sooner, and it's inaccurate because it obviously didn't in the tracker data. With drag, it almost reached the ground at the same time as the tracker data, but still slightly off. The differences here, you can see what I was talking about with the reaching the ground sooner. The tracker data only reached the ground at the exact end of the 0.433 seconds, while gravity and drag, and then just only gravity, reached them earlier. So you can see that that's why the gravity and drag is the most similar, but still not completely accurate. The errors, one of our errors is that we have probably an incorrect assumption of only two forces. We assume that there's only two forces, but seen through the graphs, we need probably some other force to fully represent our tracker data. And another error is our tracker frames. So because I have to manually calculate the center of mass of the system for each frame, there's probably some sort of error that affects the positions. So here are the what ifs and what does it mean. So what does it mean? No, none of these graphs predict the terminal velocity, because we expect with terminal velocity a non-increasing velocity at some point, but you can always see that the velocity kept changing. To design an experiment to reach terminal velocity, we want to start from a high y position, not just a meter, and probably use a different object that has a higher drag coefficient. So what if we threw it straight up, it would take longer to reach. The basic idea is that if we throw it straight up, we we convert all of our initial speed to a y initial velocity, which allows it to reach a higher position. And the higher position we can reach, the longer it'll take to reach the ground, because it's like a kinematic relative to time spent in the air is kinematically relevant to the y max position. And that's it.